press the bell icon on the YouTube app and never miss another update.
Good morning, students. In the previous class, we have started with the third topic of this unit, that is sound, and we have discussed about some introduction points on sound and properties of sound, where we have discussed about what is sound. Sound is a form of energy that causes a sensation of hearing. How sound is produced? Sound is produced by any vibrating body in a mechanical medium. Sound is a mechanical wave as it requires a material medium for its propagation. And in fluids, sound propagates in the form of alternate series and compressions. Therefore, it is a longitudinal wave. In general, when we are talk of air, when sound is propagating in air, sound is the mechanical longitudinal wave, right? And frequencies, right, audible to sound, audible to the normal human ear, are from 20 Hertz to 20 kilohertz. Sound waves of frequency less than 20 Hertz are called, right, infrasonics, and sound waves of frequency greater than 20,000 Hertz are called ultrasonics, right. Now, the speeds of vehicles, aeroplanes, missiles, etc., right, with a speed higher than the speed in air at NTP, that is 332 meter per second or 1200 kilometer per second, right, are called, right, supersonics, right. And we have also discussed some property about this sound, and most important thing is light is an electromagnetic transverse wave that does not require a material medium and it can be polarized. Sound is a mechanical longitudinal wave. It requires a material medium and it cannot be polarized, right. Now, we will take the concept of speed of sound. Speed of sound in a medium, and of course material medium. Now, theoretically, from the dimensional analysis, right, it is found that velocity of sound, right, in a material medium, whether it is solid, liquid or gas, depends upon two properties of the medium. One is elastic property of the medium and second one is inertial property of the medium, right. So, speed of sound in a material medium is found to depend on, right, number one, elastic property of the medium, and number two, right, inertial property of the medium, right. So these two property, elastic property and inertial property of a material medium. Now, elastic property means the property of the material medium to regain its original configuration after the removal of deformation force, and inertial property of the medium is the opposition offered by the medium for any change in its state of rest or uniform motion along a straight line, or a medium by itself cannot change its state of rest or uniform motion along a straight line. Now, this theoretically, not experimentally, theoretically it is found that, right. So, speed of sound in a medium is equal to square root of its elastic property by inertial property, right. This elastic property, right, is measured in terms of what is called elastic constant. Elastic constant, that is modulus of elasticity, like Young's modulus, rigidity modulus, bulk modulus, right, or it is termed as elasticity, denoted by E. Now that inertial property, right, is measured in terms of the density of medium. Density of medium. So we know that when a wave propagates through the medium, the particles of the medium execute simple harmonic motion, but the medium remains at rest. There is no motion of the medium. Only energy is transported through the medium from one place to another place. And we know that inertia of rest, remember Newton's first law of motion, right, is measured in terms of mass. Greater the mass, greater is the inertia of rest, right. But it is better to express in terms of density. Density of a body is equal to mass by volume. Therefore, inertia is measured in terms of density and it is denoted by rho. Therefore, we can write speed of sound in a medium V is equal to square root of elastic property and rho, it is equal to density, right. So this is the general expression for velocity of sound in any material medium, whether it is a solid, liquid or gas, right. So in case of a fluid, whether it is a liquid or gas, right, this elasticity E comes out to be equal to bulk modulus, that is represented by B, bulk modulus, right. Therefore, the equation becomes V is equal to square root of B by rho, right. So this is equation 1 we take, it is general for all the medium, solid, liquid or gas, or particularly in case of fluid. the speed is equal to, right, square root of B by rho, right? And now here V is bulk modulus, right? Now we have bulk modulus B, right, is equal to, it is a normal stress by normal strain. It is normal stress by normal strain, that is equal to, normal stress means it is the force per unit area by, right, normal strain, change in volume by original volume. Here F is the, right, deformation force applied normally on the surface of the medium, A is the surface area of the medium, dV is the change in volume, V is its original volume, or this is equal to P by, right, dV by V. Therefore, we have bulk modulus of a fluid, it is P by dV by V, because fluids do not have definite shape. The applied force changes only the shape of the body, sorry, not shape, size of the body, right, that is the volume. Therefore, the bulk modulus B is equal to P by dV over V, where P is pressure applied, dV is change in volume, and V is right volume, or sometimes this is taken as dP, that is the change in pressure, right. Right. Now, another important thing is, right, the bulk modulus of a gas. When we take bulk modulus of a gas, its value depends upon whether the change in pressure and volume of gas, right, take place under isothermal condition or adiabatic condition, right. So in isothermal condition, temperature of the gas remains constant while the pressure and volume change, right. And in adiabatic condition, temperature of the gas changes along with pressure and volume. So pressure and volume of a gas can change under isothermal condition and adiabatic condition. So the value of a bulk modulus of a gas depends upon whether the changes take place under isothermal condition or under adiabatic condition, right. So here bulk modulus of gas depends upon whether the change in pressure and volume of the gas take place under isothermal condition or, right, adiabatic condition, right. Number one, right, in isothermal condition, temperature is constant. Isothermal condition, temperature is constant. Now the equation of states is, equation of state, remember that, right, Boyle's law, Charles' law, right, Gay-Lussac's law, perfect gas equation which you have studied in heat and thermodynamics, right, is PV is equal to, right, constant, or PV is equal to nRT from perfect gas equation. Now in this case, right, the bulk modulus is equal to isothermal bulk modulus, it is denoted by Bi. So if the change in pressure and volume take place under isothermal condition, temperature of the gas remain constant. Now the equation of state is PV is equal to constant, or PV is equal to nRT when we apply perfect gas equation. And bulk modulus is called isothermal bulk modulus, and it is represented by Be. So number 2, so in adiabatic condition, temperature is not constant, right? In adiabatic condition, temperature is not constant. In this case, equation is PV to the power of gamma is equal to constant, where gamma is equal to Cp by Cv, the ratio of two principal specific heats of gas, right, where Cp is specific heat of gas at constant pressure and Cv is specific heat of gas at constant volume. And these concepts what we are discussing, isothermal condition, adiabatic condition, equations PV is equal to constant, PV to the power of gamma is equal to constant, gamma is equal to Cp by Cv, right? So these all things are we have discussed under the unit, right, heat and thermodynamics, right? Now in this case, bulk modulus is equal to adiabatic bulk modulus, and it is denoted by Ba, and it is denoted by Ba, right? Remember these things. Now we are going to derive an expression for speed of sound in a gas, right? So speed of sound in a gas, right, is found to be equal to V is equal to square root of B by rho, where rho is density, B is, right, bulk modulus of gas, whose value depends upon whether the change in pressure and gas, volume of gas, right, take place under isothermal condition or adiabatic condition. Right. Now we will take Newton's formula for speed of sound in a gas. Newton's formula for speed of sound in gas, or sometimes it is called, it is Newton's formula for velocity of sound in gas, right? Now, so theoretically, right, now velocity or speed of sound in a gas is, right, according to right, theoretical point of view, V is equal to square root of B by rho. Let us take it as equation number 1, where B is bulk modulus of gas, right, and rho is density of gas, right. Now we can show that from the dimensional analysis, the equation 1 is dimensionally a correct equation. In fact, this relation is derived from the dimensional method, because we know that velocity or speed depends upon elastic property and, right, inertial property. Elastic property is represented by elastic constant. All the three elastic constants have same unit and dimension, and density. So you can check it, this equation is dimensionally a correct equation, right. Now the next thing is, we also know that the value of this bulk modulus depends upon whether pressure and volume of the gas change under, right, isothermal condition or adiabatic condition, right. Now we know that when a sound propagates through a gas in the form of alternate compressions and rarefactions, that is a longitudinal wave, the pressure increases and volume decreases at compressions. Pressure, right, decreases and volume increases at rarefaction. That means there is a continuous change in pressure and volume of the gas at compressions and rarefactions, right. As we know that whenever there is a change in pressure, right, the volume also changes, right. Now if the temperature remains constant, then we can apply Boyle's law. Pressure is inversely proportional to volume of the gas provided, right. The temperature is constant, right. Now the fact is, right, when sound propagates through a gas, right, the pressure P and volume V, right, change at compressions and rarefactions, at compressions and rarefaction. Now this can happen under two conditions. In isothermal condition, where temperature remains constant, and in adiabatic condition, where temperature does not remain constant. Now from the knowledge of right, thermal properties of the materials, we know that when a pressure is applied on the gas, the volume of the gas changes, right. When the volume of the gas changes, right, temperature may change, temperature may not change. In isothermal, right, processes, temperature is kept constant either by supplying heat or removing heat. That is melting of an ice, boiling point of an water, slow expansion or compression of a gas, etc. are isothermal processes. And there are very small number of processes in the universe are isothermal. But when the pressure and volume changes, in most of the cases temperature also changes. That is, most of the processes in the universe are adiabatic processes, sudden expansion, right, explosion, sudden bursting of an inflated tire, etc. are adiabatic processes, right? But according to Newton, right, listen carefully. According to Newton, the change in pressure, right, and volume of gas due to sound waves, right, take place under isothermal condition. Now, according to Newton, right, the change in pressure and volume of the gas due to sound take place at constant temperature, right, that is T, that is under isothermal condition. It is under isothermal condition. Now the question is, why he assumes isothermal condition, right? Now here, according to him, right, when the gas is compressed, pressure increases, volume decreases, right? Now consequently work is done on the gas, right? Temperature increases due to increase in internal energy, right? When pressure is decreased, volume increases, work is done by the gas, internal energy decreases, temperature decreases. That means to say, at compressions, pressure increases, volume decreases, temperature increases. At rarefaction, pressure decreases, volume increases, right, and temperature decreases. According to Newton, the heating produced at the compressions is taken to the cooling produced at, taken to the rarefaction where cooling is produced, thereby equalizing the temperature so that the temperature remains constant, right? So now, according to Newton, the heating, according to Newton, the heat is transferred from compression to rarefaction, right, to equalize temperature, or the heat produced at compression and cooling produced at rarefaction, right, may be compensated by the surrounding so that the temperature remains constant, right? That means to say, so according to Einstein, right, the change in pressure and volume take place under isothermal condition. That is, so pressure and volume change under isothermal condition. This is according to Newton, right? Now therefore, this equation becomes V is equal to square root of B I by rho, equation 2, right, where B I is isothermal bulk modulus, right? Now let us calculate the isothermal bulk modulus, right? Now, since this temperature remains constant or isothermal condition, we have the equation PV is equal to constant. The equation PV is equal to constant. Now, differentiating this equation, this is P dV plus V dt is equal to 0. Here I am using the product rule. First function into differentiation of the second function plus second function into differentiation of the first function, and the differentiation of any constant term is 0 because its value does not change. Or we have P dV is equal to minus V dP, or P is equal to minus V, right, into dP by dV, that is equal to, right, now this is minus V dP by dV by V, and what is this? It's not V, this there is no way, you cross multiplied that one. Now this is dP by dV over V. dP is change in pressure, that is a normal stress. dV by V, normal strain, right? So this is equal to, right, BI, that is the isothermal bulk modulus, right? That is, right, where P is pressure P of gas is equal to isothermal bulk modulus, right? Now substituting in equation 2, we get V is equal to square root of P by rho. Let us take it as equation number 3, right? Now this equation 3 is called Newton's formula for speed of sound in gas, right, where P is pressure of gas and rho is density of the gas, right? Now the theoretically obtained equation is V is equal to square root of V by rho, and Newton assumed that, right, the change in pressure take place under isothermal condition, and under isothermal condition, right, the bulk modulus of the gas is equal to pressure of the gas. Here we have shown that one. Therefore, V is equal to square root of P by rho. That is the equation number 3, right? Right. So we have derived this equation V is equal to P by rho. Remember that according to Newton, it is a theoretical equation. It is not experimental equation. Theoretical formula. According to Newton, right, when sound propagates through a gas, the change in pressure and volume take place under isothermal condition. There is an exchange of heat between compression and rarefaction, where temperature increases at compression and temperature decreases at rarefaction. Due to transfer of heat between compression and rarefaction or exchange of heat with the surrounding, the temperature of the gas remains constant. So under that condition, right, Bi is equal to P and V is equal to square root of P by rho. Is that clear? Now, let us check whether Newton's formula is correct or not. Right. Now, in physics, right, different relations and formulae are derived theoretically on the basis of observation and established things. But how to confirm whether that relation is correct or not? Right. Now, what we will do, we will calculate the quantity in the relation theoretically as well as experimentally. Right. The experimental value is always true, right, because it has taken, right, by accurate measurement with very less percentage of right error. If the experimentally determined value by doing experiments in laboratory and the theoretically calculated value comes out to be same or nearly same, then we say that that relation or formula is correct. If there is a large variation between the theoretical values and experimental values, then we conclude that the formula is not correct. Sometimes we may completely reject that formula, and sometimes there may be, right, small error in formulating, right, that formula, right, or in observation or something. Then we will apply correction to it. Now let us see whether this formula, right, which is derived or theoretically on the basis of observation is correct or not. And remember that the experimentally determined value of speed of sound in air at NTP is 332 meter per second. So, point number 1, right. Experimentally determined value of, right, speed of sound in air at NTP, normal temperature or pressure, or at temperature 0 degree Celsius is, right, 332 meter per second. The experimentally determined value nearly equal, that is right. So that is, we have V experimental value is equal to 332 meter per second. This is 1. Now, right, let us calculate theoretical value obtained by Newton's formula, right. Now we have Newton's formula, V is equal to square root of P by rho, where P is pressure of gas and rho is right volume. So here, this at NTP, right, for air, right, the pressure is atmospheric pressure, right. We have pressure P is equal to rho G H, right. Pressure is measured using a barometer. At NTP, right, this height of mercury level in barometer 0.76 meter, right, now G is equal to 9.8 meter per second square, acceleration due to gravity, and rho, density of mercury liquid, 13.6 into 10 raised to the power of 3 kg per meter cube, right, and P is equal to, right, rho 13.6 into 10 power 3 into G 9.8 into 0.76, right. So on barometer scale, one standard atmospheric pressure at NTP is 760 millimeter or 0.76 meter. That pressure P comes out to be equal to, right, 101.3 into 10 raised to the power of 3 Newton per meter square or Pascal. This is the standard atmospheric pressure, that is at NTP for air, and density of air is equal to 1.293 kg per meter cube, right. So density of air at NTP is 1.23, right, 293 kg per meter cube. Now substituting the values here, V is equal to square root of 101.3 into 10 raised to the power of 3. That divided by 1.293. So V comes out to be equal to, right, 280 meter per second. That means V theoretical is equal to 280 meter per second, equation 2. Right. Now, if we compare the theoretical value with the experimental value, there is a large discrepancy in the value of right, velocity of sound calculated using this Newton's formula, right. So nearly, right, the difference is, right, 16%. That 16% variation, right, may not be due to experimental error. And one thing has to be remembered, no experiment in physics or no measurement in physics is 100% accurate. There is always some error associated with the measurement of a physical quantity, but in experiments the error is not too large, it is very small, right. So less than, right, 0.1% or 0.01%, but here the difference is 16%. Therefore this Newton's formula for speed of sound in gas, that is V is equal to square root of, right, P by rho, is completely discarded as an incorrect formula, right, because, right, the theoretical value calculated by using Newton's formula, right, and experimental value has a very large difference, about 16%. Therefore this formula was completely discarded. Right. Now, what next? Right. Now, according to Laplace, right, the observation made by Newton in formulating this formula is wrong. It is because, right, according to Laplace, the change in pressure and volume of the gas due to sound waves propagating through it do not take place under isothermal condition but under adiabatic condition, right? So, according to Laplace, the change take place under adiabatic condition, and Laplace argued that, right, or showed that Newton's observations were wrong, right? Now we will take, right, Laplace correction to Newton's formula, right? Now we have theoretically we have speed of sound V is equal to square root of B by rho. Let us take it as equation 1, right, where B is bulk modulus and rho is density of the gas, right? So here, now according to Laplace, the change in pressure and volume of gas, right, take place under adiabatic condition, that is temperature of gas is not constant. Temperature of the gas does not remain constant, right? Now why? It is because number one, right, now a gas is a bad conductor of heat. There is a bad conductor of heat. Number two, there is a quick succession of compressions and rarefactions formed in the gas. And third one, there is no time for equalization of temperature. There is no time for equalization of temperature. These are all the three reasons given. And we know that as we have discussed about conduction of heat, right? Now, conduction of heat, we have derived an expression for thermal conductivity. Thermal conductivity of a material is the ability of the material to allow heat to flow through it, right? For good conductors, the K value, thermal conductivity is very high. For bad conductors, thermal conductivity is very less. We know that metals are very good conductors of heat because of the presence of free electrons, right? So, gas is a bad conductor of heat. It is not at all a good conductor, right? That means it will not conduct or allow heat to flow through it easily. It is very difficult to make heat to flow through gas. It is a bad conductor. Number one, there is a quick succession of compression and rarefaction. Now, that velocity V is equal to 332 meter per second. Suppose we say that Now a sound of a frequency f is equal to, right, some 1000 hertz is passing through. Then we have lambda is equal to V by F from the relation V is equal to lambda F. Now this is 332 divided by 1000, that is equal to 0.332 meter, right. So approximately we take lambda is equal to nearly 34 centimeter. I am taking the round off value 34, right. Therefore the lambda by 2 is equal to nearly 17 meter, right. So the distance between compression and rarefaction is about 17 meter. That is the quick succession, the meaning of quick succession of compression and rarefaction. So in 1 second, right, the distance between not 1 second, we will take it later. The distance between the compression and an immediate rarefaction is 17 meter, assuming that the frequency of sound is 1000 hertz and speed is 332 meter per second. So approximately it is a 17, not, oh again I have written it, 17 centimeter. 17 meter is quite a large, 17 centimeter, right. Now the time lag T is equal to 1 by F is equal to 1 by 1000, that is 0.001 second. So that means to say, from these 3 points we can understand that gas is a bad conductor. Now the heat produced at the compression has to flow to compression where cooling is produced, right, in a time interval of 0.001 second. To what distance? This is 17 centimeter, right. Now that 17 divided by 0.006, that means nearly it is 17,000, right, centimeter per second. If the heat is moving that speed, then only it can reach from compression to rarefaction. Due to all these factors, right, there is no time for equalization of temperature. That means there is no exchange of heat between compression and rarefaction or with the surroundings. Therefore, the temperature of the gas changes. In fact, temperature increases at compression and temperature decreases at rarefaction. So there is a change in pressure, volume and temperature. Therefore, it is an adiabatic condition. Is that clear why it is adiabatic condition? Number 1, gas is bad conductor. Number 2, there is a quick succession of compression and rarefaction. Third one, there is no time for equalization of temperature, right. Now under adiabatic condition, equation 1 becomes V is equal to square root of BA by rho, where BA is a adiabatic bulk modulus and rho is density, right. So now under adiabatic condition, right, the equation of state is PV to the power of gamma is equal to constant. Now differentiating this equation, I am not going to differentiate this equation actually, right, with the steps, right. Now finally we come to the fact that the gamma into P is equal to minus dP by dV by V, that is equal to PE, that is the adiabatic isothermal. So under adiabatic condition, that bulk modulus of gas is equal to gamma into P, where what is gamma? Gamma is equal to the ratio of two specific heats of heats, right? Gamma is equal to Cp by Cv. It is a measure of atomicity of the gas. Its value is different for monatomic, diatomic and triatomic gases, right? Therefore, substituting in 2, let us take it as equation 2, we get V is equal to square root of gamma into P by rho. This equation is called Newton Laplace formula for, right, speed of sound in gas, and so far what we have discussed is Laplace correction to the Newton's formula. So here now we have an additional term, right, that was not there in Newton's formula, right, that is V is equal to square root of gamma into P by rho. Gamma is the additional term, right, in Newton Laplace equation, right. Now this gamma is equal to Cp by Cv, right. Its value depends upon atomicity of the gas, that is monoatomic, diatomic, triatomic, etc. So in this case, while dealing with speed of sound in gas, we have utilized the concepts of thermal properties of a gas, right, and we have used the gas laws. What is a gas law? Right, the relation connecting pressure, volume and temperature of a gas during a process is called as a gas law, right. Now this is Newton's Laplace correction to Newton's formula, and this equation is called Newton Laplace formula for speed of sound in a gas. What next? The next thing is to find the theoretical value and compare it with the experimental value. Let us see whether theoretical value and experimental value are come in agreement with each other or not. That we shall take up in the next class, right? In the next class, right, we will check whether Newton Laplace formula for speed of sound in a gas is a correct formula or not. Okay. Thank you very much.